Victor, can you start now?
Yes, I am ready.
Yes, okay.
Everything is ready there?
Yes. Start now. Thank you.
Okay, you are welcome. Okay, can you hear and see me? Everything is working?
Yes, Victor. All okay. Excellent.
Okay, very good. So, Bismillah ar-Rahman ar-Rahim. First of all, I would like to say thank you everybody for participating in my presentation. And I hope everything goes well there for you and your family, especially be far away from the current malady, the current disease, COVID-19, I mean. Okay, my name is Dr. Javad Safaie, Assistant Professor in Electrical Engineering Group, Faculty of Engineering, Ferdowsi, University of Mashhad. During this presentation, I would like to talk a bit about brain illumination, which is called in biomedical engineering near infrared spectroscopy. So when I said NIRS, you know that I'm talking about near infrared spectroscopy. You have my personal also web page address in this QR code at the right down corner of these images. So sometimes I should get a kind of feedback. Everything worked nice there. Sorry about that, just to check if everything. Okay. I don't have any feedback. Okay, so I continue like this. Okay, I would like to present a little bit myself. I got my BS degree in electronic engineering from Iran University of Science and Technology at 1998, and MS degree in electronic engineering from Haj Nasir Tusi University at 2000. During final master project, I did a bioelectric project. It has been a kind of sonography system for frontal, and it was my first connection to biomedical engineering world. After that, I created my own private company in Tehran and worked there for around 9 years. During that period, we have developed several projects, some of them in biomedical domain, sure. At 2009, I went to France in order to continue my PhD in neuroscience, biomedical engineering, and a bit more than 3 years, I got it. During my thesis, I have designed and developed a high-resolution, highly compact, wireless EEG NIRS machine, which is basically the basis of this presentation, which I would like to present for you during this course. Really. Afterwards, I continue the project for around 2 years as a postdoc, and then I came back to Iran and become an assistant professor in Ferdowsi University of Mashhad, and now I'm here to present for you something. During these years, I am honored to get several awards, which you can see in this list. Like, for example, in 2019, I became FUM, means Ferdowsi University of Mashhad Distinguished Researcher Award for Technology, and also Teacher Award for Distinguished Teacher Award for Internationalization. I got Electrical Engineering Department Distinguished Young Professor Award for Technology in 2017. Exceptional Award for Accelerating Technology Transfer Corporation from France, 2014, before coming back to Iran. Trainee Abstract Award in 19th annual meeting of the Organization of Human Brain Mapping in Seattle, United States in 2013. And I have been the winner of national competition for the creation of innovative technology company in France at 2011. So I should go to next page. Yes. During the last years, I had several courses for BS and graduated students like advanced topic in neuroscience, biomedical sensor, advanced bioinstrumentation, computer system architecture, and basics for electrical engineering. And as you can see here also, my main research interests are biomedical instrumentation, design and development, rehabilitation robot and system, home care, medical device, smart material in biomedical application, and medical standard drafting. This is the main research interest for me. And also you have my business card here. There are all contact information which may be necessary for later connection if you want. Okay, let's back to our presentation and introduction about NIRS. Around 130 years after Jesus Christ, Ptolemyus, we said in Farsi, Batlamyus, I don't know in Arabic how to pronounce it, but Ptolemyus has been one of the first men who attend to the light and matter interaction, you know, the interaction between light and material, and tabulated the refraction of light for a range of transparent material like water, something like that. Okay. After nearly more than 1,000 years, in 1305, von Freiburg simulated the structure of the rainbow by using water-filled glass sphere. He put a kind of glass which is filled by water on the sunlight, and he could generate a rainbow on the ground or on the paper, something like that. In 1800, or 1800, William Herschel, who has been a German musician and also a very good astronomer, he wrote two papers detailing his study for the heating effect in the spectrum of solar radiation. What I want to say means, as you can see in this image, he put a prism in the front of sunlight and got a rainbow on a black paper. It's clear in the image. Okay. By this experiment, he would like to measure the amount of heat which is produced by different light color. So he put his thermometer on different color band and measure the generated heat. Like this, he would like to measure the energy of different light color. One time, accidentally, he put his thermometer just after the red, in the black side. I would like to know, can you see my mouse on the presentation? I'm turning my mouse here. Can you see it? Is there anybody to answer me?
Yes, Doctor, no, not a problem, yes.
You see my mouse, my
yes.
pointer?
Yes, yes, yes.
Okay, very good, because I would like to use it. That's great. Okay. You know, thank you. He put accidentally his thermometer here, and normally he expects that the thermometer should be quite cool because there isn't any light here. But he found that the biggest amount of energy, the biggest amount of heat is generated in this area. And he put the name of infrared for this area. Means some part of light which is not visible, but there are something there. Okay. The idea of using the near infrared light, NIR means near infrared light, to monitor physiological phenomena arises in 1977 by Jobsis, when he discovered that NIR photon, near infrared light photon, could penetrate in relatively dense tissue, including skin and bone. You know how he did the experiment? This is the curve who has the Jobsis published in his paper, the time course of the response to hypoxic episode of intracranial hemoglobin and blood volume in trans-illuminated cat's head. He put some light from one side and put one detector from other side in the head of a cat, and he present a kind of hypoxic episode and measure something, and he got this kind of curve, which later I will explain about that. But however, the father of NIRS technology in biomedical engineering is Jobsis. Just remember this one. Okay, here you can see the electromagnetic spectrum. It begins from very high frequency, which normally is gamma radiation. You can, excuse me, I have to come back again. Yeah, here, the gamma radiation means the highest frequency or lowest wavelength. Okay, you know the relation between wavelength and frequency. By decreasing the frequency, we are X-ray band, and then UV means ultraviolet band, and then we arrive to visible band, visual band, which started from violet, then blue, and finally we reach to red light. And then after red light, we have a relatively big band of infrared, which started from near infrared, from 700, around 700 nanometer, up to 1000 nanometer or 1 micrometer wavelength, and short wave infrared, middle wave infrared, long wave infrared. There is a big band about infrared radiation. And then we have microwave, you know it. We have radio communication wave like FM radio, AM radio, and then finally we arrive to lower frequency like electrical power, 50 hertz, something like that. Okay, you know that the nature of the electromagnetic wave are the same. Just what is the difference between AM, FM, I don't know, optical range, which can be seen by a human eye, and gamma and X-ray? It's just the frequency is different between these different type of radiation. Okay, and we will, biomedical engineers normally use different part of this spectrum, which later I will explain about that. Okay, let me check. Okay, here you can see different type of application which we can define in biomedical engineering. Normally, we have two types of direct and indirect. The direct method are used for treatment. Indirect method normally used in diagnosis. For sure, you can split the techniques in different ways. So this is not fixed, really. This is one of the categorization which you can do. You know, for example, we can have a photodynamic therapy. we can have a laser surgery, we can have a thermotherapy, we can have an optical biopsy, we can have an optical tomography, and also we can have an optical spectroscopy, which we are here. And we would like to explain a little bit about this red circle here. Okay, here you can see the light-matter interaction. Means when some photons of light reach to a matter. This is not a problem. Which type of matter? Maybe mirror, maybe glass, maybe water, maybe tissue, which we would like to discuss about that. Normally, we have 4 types of interaction. We have reflection. You know it very nicely because in mirror you have it every day. So change in light direction at fixed angle. We have transmission, what happened in normal glasses, for example. We have also 2 other phenomena which is very important in near infrared spectroscopy. One of them is absorption and one of them is scattering. These 2 later phenomena is very important for us here. What the meaning of absorption? Absorption means when a photon goes inside the tissue, for example, the body, these photons make a kind of impact by a molecule and then disappear. The energy of this photon convert to a kind of a little bit heat and Jobsis, and there isn't any photon anymore. Okay, so this is the meaning of absorption. And the meaning of scattering means when the photon goes inside the tissue, it hits a kind of a molecule, and based on the size of molecule or the size of cellule or the wavelength of the photon, this photon change the direction of movement. So it goes to another direction, you know, and by hitting the another molecule, maybe change and again the direction, and this kind of changing the direction we call scattering in tissue, which is very important for us in near infrared spectroscopy. Again, I will explain it later. Okay, here, in order to have a sense about scattering and absorption, I have presented a very nice experiment here. You can do it sure at your home, you know. In the left side, you see a kind of a glass, which is glass cup, which is covered, which is filled by water, like this one, for example. I had a tea here. So if I put this one, the glass cup in front of my eye, for sure I can see the other side of the glass. Okay, if I put some water inside, again I have the same story, I can see the other side. But if I put some ink, black ink or India ink inside the water, what will happen, you think? For sure you know it. Still you can see the other side of the glass, but with less light intensity. You know, it works like sunglasses which you put outside when you are hell amount of sun in the air, you know, for protection of your eye. So this is the story of the Indian ink, black ink, because the dimension and the size of molecules, you know, the Indian ink, the black ink, absorb some part of photons, but the rest they transfer from other side to your eye, and still you can see the object on the other side of the glass. Okay. As soon as you put another important matter is when a photon comes from this direction and goes inside, some photons get absorbed by the internal liquid, which is a black ink, and someone comes out and reach to my eye. And the distance the photon goes from this side to this side is exactly equal to the thickness of the glass. We agree with this one, okay? But as soon as, okay, you can assume, you can do another experiment. You can put again some fresh water inside the glass and just put some milk Intralipid here means a special kind of milk. As soon as you put some milk inside the water, it is impossible to see the other side of the glass. Why? Because the molecule, the size of molecule of milk is a little bit special, and the wavelength of the light which wants to come to my eye is again a little bit special. In between, the phenomena of scattering is happened, you know. So when photons come from this direction and wants to reach to my eye, you know, the photon inside go like this, like this, like this, like this. Scattering happen in hell amount of direction, maybe 1 million times, something like that. And finally, when the photons go out and reach to my eye, there isn't any information from the source of photon. So it is impossible to see the other side of the glass. And this experiment is very easy, and you can do it at your home. And another nice story is the path length of photon. Means when the photons come from this side of the glass and wants to reach to my eye, normally the thickness is L, for example, but the path length of the photon is much bigger than the L, because the photon goes like this, like this, like this, like this, like this inside the milk, and then finally comes out. Maybe from other side comes out, maybe from this side comes out. So this is the basic nature of scattering and absorption. I hope everything worked nicely for you and you understand what I want to say about these two very important phenomena in near-infrared spectroscopy. Okay. As you know, the light has a kind of dual nature. What I want to say means sometimes the light acts as a kind of electromagnetic wave. Sometimes the photons, which is created the light, they act as a kind of a small packet which carrying the energy. So this is two type of nature which we can consider the light, and in each case we have different history about the light. For example, as you see here, if we take care of the light as a wave, we consider light as electromagnetic wave, especially when describing the polarization, phase, and interference. This type of matter are important when we talk about the wave. This model convenient for describing light-matter interaction on the macroscopic level, such as reflection, refraction, etc., which is not very important for us in NIRS. And when we take care of light as a wave, the electromagnetic wave theory is there, and we should solve the Maxwell equation in order to know what happened in the light-tissue interaction. When we take care of the light as a kind of particle, means the light is not electromagnetic wave anymore, but there are many photons carrying discrete packet of energy. This model is well suited for treating light matter interaction on a microscopic level, which is important for us here. For example, energy transition in atom, molecule, and light tissue modeling. The later one is our discussion. Here, normally we have radiative transport theory, and radiative transport equation we should solve in order to understand what's happened between the light, photon, and tissue. Okay. Honestly, I don't want to go to mathematical detail. You know, if you see the name of my PowerPoint, at the last part, I put one R, means reduced version. Just last night, I had many images, many presentation pages here, but I discard some of them because I thought that this is not may be a good idea to go deep inside the mathematics here, just to say something, but I have to say also something, just in order to have a kind of sense from what we are discussing about. Okay, so we have three important parameters which I would like to explain for you. One of them is absorption coefficient. What the meaning of absorption coefficient? Assume that this dotted line here is a boundary of tissue, and the light from the outside from here going inside the tissue. Just by chance, some of photons get absorbed after a small walking in the tissue. Some of photons can go deeper, and some of photons can go deeper and deeper and maybe can go outside from the tissue. This is just by chance. Can happen, and we can define a kind of absorption coefficient, which is the inverse mean of free path length. This one is a free path length 1, the shortest one, and this one is a free path length 3. The mean of this one, if you not the mean really, if you add all of this one, but this is the mean, the inverse mean, I divide by all the summation of free path lengths, it becomes a kind of mu A, which is called absorption coefficient. We can also define this absorption coefficient based on another theory, which is not important at the moment for us, so we can forget about the right part. Okay, we have the same story, exactly the same story about the scattering coefficient, which is mu S. Again, when the light goes inside the tissue, some photons get the first scattering effect. Here we are talking about the first scattering. For sure, in absorption, the first absorption will be the last absorption event for a photon also, because after absorption, we don't have any photon anymore. But for a scattering, no. A photon can have several 100 million milliard of scattering inside the tissue. So this is not a question. So when we are talking about scattering event, here means the first scattering event. So a photon then goes inside the tissue. Some of them get the first scattering event just in some maybe micrometer, and some photons can penetrate deeply in the tissue without any scattering. So means they can go directly like this inside the tissue. And the mean of this free path length for a scattering, we can create a mu A. In this case, for example, mu S, excuse me. For example, when you said that mu S is equal to 25 per millimeter, means normally all the photons get the first scattering at 0.04 millimeter after entering the tissue. So this is the meaning of a scattering coefficient. The third important parameter is G factor, which would like to say us something about anisotropy or asymmetry factor. What is the anisotropy? Means when a photon, you assume that a photon comes from this direction, and this is a molecule or a cellule. When the photons hit this one and wants to change the direction, okay? So means my hand here is a kind of molecule here. A photon comes like this directly and hits this one and wants to change the direction. Which direction? Like this, coming back like this, go down, or go a little bit straight like this, or like this. Which kind of direction? Isotropic scattering, excuse me, I have to come back. Isotropic scattering means the probability of a scattering of this photon is the same in all direction. Maybe the probability to go in this direction is equal to go in this direction. In all direction, you have the same probability. So in this case, you say that the G factor is 0. So it's a cosine of mean of all scattering angle. And if you have anisotropic scattering, same as the right one, it means when a photon hits this molecule, the probability of going just straight like this is much more than the probability of coming back like this. You can see in the image, you know. And we said that, for example, in this case, the G factor is around 0.9. Means the angle, the cosine of angle is near 1. So means much more photons would like to go straight like this in the tissue. So this is we call G factor. Normally for human body tissue, the G factor is around 0.9, something like that. Okay. So we are talking about absorption and scattering. At the moment, you know something about absorption and scattering, and you have a kind of sense about them. And here I put two axes. One axis is wavelength. You know that 400 nanometer is for around something like a blue-green color, something like that. And 700 nanometer is red color. And after 700 nanometer, the history of infrared begins. So infrared begins from nearly 700 to later to higher wavelength. And the other axis is absorption. When the absorption is high in this area, for example, or in this area, what does it mean? It means that many photons which you inject inside the tissue will be absorbed by tissue in this wavelength. So what this image wants to say to us is that just there is a small area in the middle here where the absorption coefficient, or when the absorption is decreased, and in this area, in this amount of wavelength, for example, from 700 to 1000 nanometers, something like that, in this area, the photons can go deeply in tissue without getting any absorption. Why? Because the absorption coefficient is low. So it means that the photons can go more and more in tissue without any absorption. This is very important for us. I will explain it just in the next page. And what I have present here, I present water, you know, because typically 80% in adult brain tissue is water. So it is very important. Absorber, you know, in infrared range after 1000 nanometer, the absorption of water becomes high and high. So we cannot go in tissue by this wavelength. And also we have another kind of chromophore. What the meaning of chromophore means? Small particles in cellule which create a color for cellule. We say chromophore. For example, in blood cell, we have different type of chromophore. We have HBO, means oxygenated hemoglobin. What is the meaning of oxygenated hemoglobin? Means the red blood cell containing the oxygen coming from lung, and once go to different tissue, especially in the brain, which we would like to discuss about that, you know, for metabolism of cellule. And when the HBO deliver the oxygen to cellule, it becomes HB, means deoxygenated hemoglobin. So the deoxygenated hemoglobin means the blood cell without oxygen. which wants to come back again to heart and come back again to lung for getting, renewing the oxygenation process. So you know this one. These two important chromophore, which we would like to know about them by NIRS. As you see here in this image, the absorption becomes very high at lower wavelengths. Means this is why by blue, for example, light or green light or this type of light, we cannot go inside the tissue because they get rapidly absorbed by the human tissue. So it is impossible to go to see the inside the tissue in the non-invasively. Okay, and also we have a kind of another chromophore like lipid, for example, like melanin. You know, melanin is the main important part of the skin, which create the skin color, really. Okay, and melanin is a kind of very strong absorber for us, but fortunately, the absorption rate is fixed. Means if it absorbs 10 photons at this moment, it will absorb 10 photons again 1 second later. So there isn't any change in photon absorption by melanin. Also, we have same story with lipid. Most probably, we have the same story with water in a small timing period. Just the hemoglobin concentration change. This is very important. What I want to say means by beating the heart, when the heart is beating, you have a hell amount of oxygenated hemoglobin at the moment, at one moment, and then decrease, and then increase by beating the heart, and then decrease. So the amount of oxygenated and deoxygenated hemoglobin is changed at least by heart beating. Okay, so we have another history for hemo-oxygenated and deoxygenated hemoglobin. Okay, in this image, I would like to present a concept of optical window. What is the meaning of optical window? Means just the narrow band, which I explained to you, from around 700 to 1000 nanometer. And because of the absorption coefficient is reduced in this area, we can go deep in tissue. And this is why they put the name of optical window for this range of wavelengths. And because the lower amount of absorption, the photons can go inside the tissue and come back again like this. Okay. Okay, again, we come back to spectrum. As you know, we have different type of imaging system. In gamma ray band, we have a different type of technology like PET, positron emission tomography, or SPECT, single positron emission tomography. In X-ray band, we have CT, or computed tomography. In visual band, we have OIS, or optical intrinsic imaging. In near infrared band, which is started from 700 to 1000 nanometer, the optical window, you remember it. We have NIRS, or near infrared spectroscopy. So at the moment, you know that where we are when we talk about NIRS, where we are in the spectrum. After that, we have TES, means thermoencephalography. In this area, we use this technology in this band. And then we have MRI, means magnetic resonance imaging, because you know that the MRI machine, they use radio frequency for different coil in order to stimulate the spin of hydrogen atom inside the tissue. I don't want to go inside this one. And also in lower frequency, we have, for example, EEG, electroencephalography, which is in range of several hertz or several 10 hertz, finally, something like that. So we have different type of imaging technology. And you know that where we are when we talk about NIRS, near infrared spectroscopy. Okay. I have a kind of animation here. Just I would like to know that, can you see this animation? There is a one coming photon from NIR, means near infrared light source, a small yellow ball. Can you see this one? It would be great if you can give me a feedback. Hello, can you hear me? No one is there?
Yes, of course, we hear you.
Okay, so the animation is working for you also?
Yeah, of course, it's working.
Okay, okay, very good, very good. So, what I want to say, what I want to show to you in this animation, I want to show the principle of NIRS, how it works. When we say NIRS working, what I want to say. Okay, this is the you can assume that this is my brain here. Okay, so we have scalp, we have CSF inside the brain, and finally we have brain, means mainly cortex. Okay. You know that inside cortex there are two networks mainly. One is neural network, which works basically electrically. The activity is electrical activity. And we have another network, which is vascular network, means the vessels, you see here in this area, the vessels which produce the blood, the energy, the oxygen, the glucose, something like that, for the neurons. Okay, you know everything here. And in this case, we would like to put one emitter just here and one detector just here, something like that. Okay, assume this type of emission and detection. Okay, when we send some photons inside my brain, what's happened? If there isn't any scattering matter there, the photons goes directly inside my brain, and after some walking, get absorbed by some molecules. Okay, but as soon as you have some scattering, it moves like this. You know, it gets scattered. But this is the one, just one scattering. If we have more scatterer, it goes like this, you know. Some photons get absorbed by HB, means oxygenated hemoglobin, red blood cell, which contain oxygen, and this is HBO, excuse me, and HB means again the red blood cell, but without oxygen. So oxygenated hemoglobin, deoxygenated hemoglobin. Okay, and as soon as you have more scattering, something like this happens. Some of the photons get scattered inside the tissue, and accidentally some of them come back and can get absorbed by the detector. This is the principle of NIRS. Okay, so in NIRS, we send, for example, 1 million of photons inside the tissue. From this 1 million, maybe 100,000 of photons get absorbed by blood cell, tissue, different things. And many of these photons come out from tissue. But for example, when you put the detector here, if photons come from this area, you cannot detect this one. If you come out from this area, you cannot see it. Or if you come out from just the photons come from this area, you can get these photons here. Okay, so many photons come out from tissue, but just a small part of this one can get absorbed by the detector. Okay, what is the principle of NIRS? Maybe it's a good idea to explain it here in this image. I have other images also in the next pages, but here it's quite nice for this one. Okay, so assume that we have 1 million photon inside, and for example, 1,000 photons we can detect by detector. Okay, so if I start to solve a mathematical question, for example, it means that the frontal part of my brain here engage in the solving of this mathematical problem. So the neurons in the frontal area start to work much more than the rest position. Okay, so in this case, the neurons want to work much more because they want to solve my mathematic question. So because they want to work, they need much more oxygen. What is meaning? Means the vascular network, the vascular system should prepare much more oxygen, oxygenated hemoglobin inside this area. And as soon as you have much more oxygenated hemoglobin in this area, it means that the probability of absorption of the photons will be much higher. Means if in the rest state, from 1 million photons goes in, you have just 1,000 come out. In this case, you have 900, 800 comes out. You understand what I want to say? So by this change in amount of detecting photons, we can understand that what's happened inside the brain. This is the principle, physiological principle of near infrared spectroscopy. Later also I have another images about that. And there is another concept which if you read some paper or some books about the NIRS, you have the concept of banana shape. What is the banana shape? Means the area of the photons which goes inside the tissue and can be detected by the detector. It creates a kind of banana inside the tissue, but it is not quite same as banana. But however, they set it as a banana shape, which is the way, the path length of the photon inside the tissue. So you understand how it works. Okay, this is what I said before. We have two types of network in the brain. One network is neuronal network, which is mainly work electrically, electrophysiologically. And another network is vascular network, which prepare energy and oxygen for this neural network. Okay, and there is a kind of neurovascular coupling. Means as soon as you start to think about a mathematical question, as soon as you start to think, the neural network start to work much more. And for this one, the vascular system behind start to work also for preparing oxygen and glucose and energy for this neural network. This is a neurovascular coupling, which is very nice. There are some very nice theory behind. Also, it is very important in research domain, you know, because sometimes in special case, for example, you know what is epilepsy? The patient who sometimes get like this and they fall down and something comes out from their mouth. This is the a kind of malady, disease, which name is epilepsy. Okay, in the epilepsy, a kind of at least in the generalized epilepsy, a kind of spike start to work in the brain, and it cover whole the brain, and this is why the generalized attack of epilepsy happen. Okay, it's funny. Before starting the electrical activity, the neural activity is starting. The vascular activity is starting. Means if you monitor the brain of this kind of patient by NIRS, you can understand some second before a start of seizure, just some seconds before you can understand that the seizure will happen for this patient. This is very important matter. It means that the vascular network start activity just some seconds before neural activity, you know. So there is a quite complex and unknown relation between these two types of networks here, which you can go deep inside. Okay, here we have a kind of a principle again of NIRS, and we would like to know that how it works. You see here, we have some red blood cell contain oxygen. They come in the tissue. Here we have some neurons. They are working, so they consume the oxygen. So this red blood cell deliver the oxygen to tissue and become blue. Not really blue, but means that they don't have any oxygen anymore, so they have to come back again to heart and their lung for renewing the oxygen cycle. So please read the text here. Neurons consume energy, means glucose, when activated, when you think about something, or when you move, for example, your finger like this. When you move your finger like this, what is meaning? It's meaning that this is my right hand, I'm moving my finger like this. So some part in motor cortex in left side, some part like here, it start to move to activate my finger, you know. So this area of my brain, this area just here, you see, just here is activating now. Now it is in rest. Now it is activating. You see, what is the meaning of activating? Means this area wants to move my finger. So in this area, I have more consumption of oxygen, more consumption of energy in this area, you know. And as soon as, okay, so let me click on this one. So as soon as you start to do something like this, and the neurons need more energy, the vascular system, the vessels become larger, bigger like this. Why? Because the amount of blood, the amount of red blood cell comes to tissue become much more. And by this, the vascular system compensates the oxygen which is needed by the neural system. You see, as soon as you start to move your finger like this, in this area, the amount of oxyhemoglobin, you see the upper curve, the amount of oxygenated hemoglobin comes down, means the tissue, the neurons, start to use the oxygen, but still the vascular system, the vessels, are in normal situation. They don't understand what's happened. So the amount of oxygen comes down. As soon as the vascular system knows what's happened, the vascular system start to become larger, and the amount of oxygen comes inside, become bigger and bigger, higher and higher, excuse me. And we have a phenomenon which we said overcompensation. What is the meaning of overcompensation? It means that as soon as you move your finger, a little bit, the oxygen consume a little bit more, so you have less oxygenated hemoglobin. But as soon as the vessel starts to become larger, the amount of oxygen become high, and it's a like of overcompensation. And you see that the time course of this event is in the range of seconds. Okay, it is not same as EEG, because in EEG, electroencephalography, you are talking normally about milliseconds, but here we are talking about seconds, because the response of vascular system is slow, and the vessels, they cannot become large and again come back to their initial size in millisecond range. This is not possible. So you see how it works. And what induced hemodynamic response? We say to this one hemodynamic. This is a or metabolic response or hemodynamic response. What is induced this response? Different type of stimulation. For example, somatosensory. What is the mean? For example, if you put a kind of somatosensory stimulation here and you stimulate the finger, for example, by median nerve here, okay, or auditory stimulation. At the moment you hear my voice, so it means that there are several parts of your brain engaged in the data processing. The first is temporal area. This area of brain engaged in processing of the words, not out of the words, of the phonemes mainly. Okay, and much more lateralized in the left side, means much more here. Okay, and then the network is come mainly on the frontal part, on the here, for a higher cognitive understanding. If you want to exactly understand what I want to say to you, you need a higher level of processing, so you transfer all the information to frontal part. So this part again engaged. So by my auditory stimulation, different part of your brain is stimulated really. So different type of stimulation. When you see my figure, it means that in the occipital part, in the back side of the brain, you have some stimulation and so on. Okay. What I said, you can see it here again. This is again the same story. I don't want to go to fNIRS concept. It's a little bit complicated for us at the moment. But the slowness is exactly what I said to you. And so you have a vascular level and you have absorption, change in absorption. When you increase the hemoglobin here, you see, when you are in this area, when you increase or decrease the amount of hemoglobin, red blood cell, means you increase or decrease the amount of absorption in the tissue. So the amount of coming back photons from my head, you remember 1 million in, 1,000 out, and by changing of this one, you have sometimes 1,100 when it comes down, and you have 800 when it comes up like this. Okay, so by measuring the amount of photons coming up from the tissue, you can find this curve, and you can guess the amount of oxygen consumption by underlying tissue. Okay, so this is done. Okay, up to now I talked about the basic of the NIRS. From now I would like to talk a little bit about technology, and mainly what I did during my PhD, honestly, and after that what I did in Ferdowsi University of Mashhad. Okay, when I start my study in PhD in France, the first question has been the cap. It's funny, it is very simple. It looks like to be some simple things, but it is very complicated. I have 2 US patents just about the cap. It's funny, huh? Okay, so what the meaning of what I want to say by cap? You for sure you know you see different type of EEG cap as you see in this image. We have different type of EEG cap. They are mainly created by tissue. Okay, like this, not the human tissue. I mean some clothes like tissue like this. Okay. And they have different size. For example, you have some size for neonates, some size for children, sometimes for adults, something like that. And when you put this tissue over the patient head, you put the electrode inside, and normally you use electrolyte gel, you know, and because of electrolyte gel, the life becomes so easy. Why? Because the electrolyte gel create a nice contact between the skin and the electrode. Like this, you can record the electrical activity of the brain, which is called EEG activity. But for NIRS, the history is quite different. Why? Because, for example, the main problem in EEG, the hair, for example, I have a black hair, you see. This kind of hair is not any problem. Why? Because as soon as you inject a little bit gel, the gel goes inside the hair, you know, and make a contact between the electrode and the skin. Okay, but in near infrared spectroscopy, this is not the case, because you have light, so you should inject photons inside the skin. So if you put something over the hair, and especially for me, black hair like this, it is impossible to send some photons. Even if you can send some photons inside, where you want to put your detector? Just, you remember, from 1 million photons, just maybe 1,000 photons comes out. And how you want to detect this, collect this 1,000 photons? So you should go between the hair, you know, and reach to the skin, directly to the skin. And even at this situation, the root of the hair will create many problems. But however, so you understand that this is not so easy. From another point of view, because you want to inject the photons, the emitter and detector should be perpendicular, like this, not like this, not like this. It should be exactly perpendicular to the brain, you know, because, for example, here you have an emitter, here you have a detector. If they become something like that, so the photons go directly like this to detector. So there isn't any information about my brain inside these photons. Okay, so it's a quite complicated history about the cap. I will explain a little bit more about the cap and what I did personally for cap. I would like to explain it because it's a really challenging debate, you know. So here I put two red lines, which is nice for me. The EEG cap, the NIRS cap, excuse me, should be flexible. Why should be flexible? Because should cover the head. We have different type of head, different size, different shape, you know. So it should work for everyone. And from another point of view, it should be rigid. Why should be rigid? Because the emitter and detector should be kept in place just like this, without any movement. As soon as you move this one, hell amount of movement artifacts will be created inside your recorded signal. Okay, so the cap is very, very important as a kind of bottleneck for near infrared spectroscopy technology, for NIRS technology. So again, NIRS cap should be flexible, should be rigid. You know what I want to say. We designed a different type of arrangement for our work. First of all, I thought that, okay, we have different type of requirement. You should take care of this requirement. One of them is functional requirement, means the cap should work. This is very important. Another requirement is operator requirement, means the nurse or the operator can be fixed the cap easily over the patient head. And from patient point of view, we have several patient requirements, means the cap should be take place very easy over the head and shouldn't make a kind of pain or disturbing the patient, this kind of thing. It should be very easy to put without any pain, without any pushing in some point, something like that. Okay. Based on these requirements, we have designed 5 types of strategy, which I would like to explain for you one by one. The first strategy has been individual cap, complete cap. The second one, EEG cap with electrode. Then the next one has been hexagonal structure, strap structure, and solid state strap structure cap, which I would like to explain to you. Okay, the first one has been individual cap. What I want to say, as soon as you have the patient in, you have a patient in hospital, you can take some photo, okay, by camera from the head, or if you have the MRI of the patient, In this case, you can create a surface by the photo, by the camera, or by MRI image. You can create a surface of the patient head, and based on this surface, you can see on the left side in the left image, you can generate a mesh file, and by this mesh file, you can generate. You can use this mesh file for generating or creating or printing, 3D printing, a special cap for this patient. For example, this is the neonate. You see the eyes here and the nose here, you see. And we generate the mesh for this one. And just based on the head of this baby, just for this one, we create this model. And finally, this one, we 3D print it. And this would be the best ever cap for this patient, but there are some problems. It takes at least several hours, because as soon as the patient comes, you need to take some photo, you need to generate the mesh, you need to 3D print, and so it takes several hours. And also it is costly, because you should do everything for each patient, okay? The next strategy has been electroptode. You know, electroptode is a keyword which is produced by our team, really. This is our keyword. We have submitted also in this keyword in Europe. You see, this is a normal standard EEG electrode, EEG cap. You know, the white plastic component, we put the EEG electrode inside this one. We create electroptode component. It's a plastic component like this. Just we can remove this white plastic and put this one. From this area, you can insert the EEG electrode. As you know, there is a hole inside the EEG electrode. So from upper side, you can put the fiber optic. You see this one. This is 2 fiber for emitter, and this is a detector bundle fiber. So you can put the fiber optic inside these components. These two are our electroptode components. And by this one, you can have EEG and NIRS at the same time. This is very important. Over the patient head. So this has been the next strategy. The next one has been a cap with hexagonal structure. This is very nice. I really like it. You see here the structure is a hexagonal structure, same as the B, create home. You know what I want to say. You know, there are several components. This component is designed for EEG electrode, this one for NIRS detector, this one for NIRS emitter, and these components are connection components, you know. And finally, you can create a structure like this. As soon as you put over the patient head and you fix it from a side strap like this, it works perfectly and can take the NIRS fiber optics over the patient head at the same time with EEG electrodes. Okay, this one has been the next structure, which is patented at 2012. You see, we designed a very nice structure. I'm really proud with this one. You see, there is one central chain which is placed from nasion here. This is a central chain. Placed from here like this, over the inion here. Okay, there is a central chain like this, and several lateral chain. You see the lateral chain here, and because of the structure, the designed structure here, all the chain stay perpendicular to the brain. If it comes in front, it stays like this, perpendicular. If it goes like this, it stays again like this, perpendicular, everywhere. So it is a generalized cap, which is work perfect for EEG and NIRS. Another very good point of this cap is that it has an open structure. What's the meaning of open structure? Means you can see here, between the white lines, you have access to patient hair. What I want to say means you can remove the hair by some little things like this, for example. You can remove the hair, and you can be sure that the optical fiber reach to the skin of the patient. You remember the problem of NIRS, which I talked about the hair problem. Okay, so this open structure is very helpful. For example, let me come back. In EEG cap like this, in EEG cap like this, you don't have any access to hair. So if some hair goes between the emitter and detector and the skin, how you want to remove it? It's very simple, but you cannot remove it. Just like this. But with this structure, with this open structure, you can easily remove the hair, the patient hair. You know, this guy has been, Roman Plasterman, he has been my technician in that lab. He has a very small hair, but you assume you want to work with a girl, with a woman, with hell amount of hair, especially the wounded hair, you know. So it's really difficult to put the sensor, emitter, and detector over the skin. So it's really difficult stuff, you know. So we created this one for a fiber optic, and also by changing the component like this, you can have a solid state cap, means LEDs as an emitter, you see here, and detectors and silicon photodiode with integrated amplifier as a detector. I will explain later. And this is the last strap structure cap, which is patented, US patented at 2016. You see, this is my final system. You know, the cap with central chain. There is a channel here for guiding the wires. The components are placed like this. And this is the box. You know, this box, you can see it here. All the electronic, everything integrated here. This is also very important because I put a high resolution EEG and NIRS machine inside a small box like a cigarette box. This is why I said highly combined, highly integrated system. So we did also very study about the curvature. For example, this area. This area is flat. This area also is flat. But what about this area? This is a curve here, you know. And the component which you put here, maybe they become painful. And as soon as they become painful, it's not possible to use it. You know, it's very funny. If you put your finger like this over the skin and keep your finger for 1 hour, for example, the red blood cell comes here, you know, and like this you cannot record near infrared spectroscopy signal. This is impossible. So it is very important to know that if you put this band like this here, where is the maximum pressure you see here? The maximum pressure, for example, you have on the curvature like this, you know, and you should take care of these components because this area could be very painful for patient. Excuse me, my camera is there, so normally I'm looking there, but I know that you are there. Okay, so yeah. This is the first NIRS system which I have designed in France, you know. The block diagram of the system is something like this. We have a radio communication system because I would like to design a wireless board with a Bluetooth dongle. You have a connection, wireless connection to laptop. And then you have a microcontroller, microprocessor. In the first version, I had a FPGA. You see the big FPGA here. And I have some light source driver, which means that they drive the LEDs, dual wavelength LEDs. And we have a light detector, we have a programmable gain amplifier, and we have a high resolution analog to digital converter, and we have a power supply module, and finally radio module. You can see the radio Bluetooth module here over the board. Okay, and you see the dimension of the board comparing to little paper clip here. You know, and by this we did the first experiment of near infrared spectroscopy recording over the patient head. This has been the final system for my PhD, but not for postdoc. In this system, I combined high-resolution EEG and NIRS system, 32 programmable light source, 32 detector, and 16 channel of EEG, plus 3D accelerometer. You see, this part of block diagram is exactly the same as the previous one, but we have also EEG. ASIC means application-specific integrated circuit, a special chip for EEG recording, which is here, this one, in the board, if you want to see. And finally, ADC and 3D accelerometer. 3D accelerometer has very nice story, because you know that, for example, when you want to have a 1 hour, 2 hour long-term recording, normally the neonates, the children, they move their head like this, you know. It is impossible to ask someone to keep the head just like this for several hours, okay? So they move the hair and the head, and this movement make many movement artifact in the signal. We put a small 3D accelerometer over the head, so as soon as the patient moves the head, we have the movement information, means the acceleration, means the velocity of the movement, and based on that, we can mark a special part of data on the software, you know. Okay, and this has been the report, the result of the recording of system. Here on the upper side, you can see the EEG. You know, in this experiment, I asked the patient to move the finger like this, but not asked by, honestly, by median nerve stimulation. And we had a patch on the left side, as you can see here. There are 12 EEG electrode, which is placed on C1, C3, C5, T7 position. You know this one. And also 2 lines of NIRS, near infrared spectroscopy, and all of them work at the same time. This has been very nice at that time, at 2013. You know, and this is the EEG signal, and this is the NIRS signal, and you can see very nice compatibility between the EEG positioning. The EEG shows the center of activation here in the brain cortex here, and also we have much more better spatial resolution compared to EEG from the NIRS here in this area, you know. And this one, okay, nearly done. This system, when I came back to Iran, I have created this system, this NIRS, which I put the name of Optical on this one. This system is commercialized at the moment, and I have several systems like this to some Iranian university and research centers. You know, there is a software like this. As soon as you put the emitter and detector cable, you can put the there on the frontal part, and you have the signal here, you know, for 2 detectors in the right and left hemisphere. And I will show you something more about this one. You can do different type of experiment by with NIRS. Some of the main experiment could be done over the head on the brain, but also you can do some experiment on the muscle. How? In this image, you can see we put a cuff on the upper arm. Let me show you. On the upper arm like this, we put a cuff, and we put a NIRS emitter and detector on this muscle. Okay, we inflate the cuff and make a high air pressure on the cuff, so the artery and vein, both of them are closed here. As soon as you close this area, what it means there isn't any blood goes in to tissue and come back. So the blood amount here is fixed. it means that the amount of oxygen is fixed, but the tissue consumes the oxygen. So the amount of oxygenated hemoglobin comes down, and the amount of deoxygenated hemoglobin comes up. You see here in this curve, it's very nice. The blue one is the HBr, means deoxygenated hemoglobin start to come up as soon as you pinch off, as soon as you close the cuff, and the amount of oxygenated hemoglobin comes down, you know, and as soon as you remove the cuff, you deflate the cuff, you open the cuff, so the blood goes directly like this. After 2 minutes of pinch off, the blood goes directly in, and the amount of oxygenated, you see the overcompensation. You have a kind of overcompensation for oxygenated and like this for deoxygenated hemoglobin. So with this instrument, you can, with the NIRS technology, means you can do also many experiments on muscle also. Here again, I said something to you about the mass. You see here, the pink area means we ask from a student to sit down like this. Okay, we put a patch, NIRS patch on the frontal side, like here, as you can see in the image. And we ask him to be at rest, for example, like this. Rest, 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 like this. As just at this moment, we put one paper with 3-digit by 3-digit multiplying and ask from the student to multiply these two numbers. He start to multiply, you know, and the frontal part is activating. And then after 20 seconds, we take off the paper and ask from the student to be in the rest situation again. And again, we put the paper, again, we ask to rest. You see, you understand what I want to say? This is the stimulation period, really. And here I have a nice movie to show you. You see, I play the movie. Be careful about the frontal two detector, right and left hemisphere. You see, we have much more activity in the left hemisphere. You see, this is a blood activity. This is a hemodynamic, metabolic activity, means there are a hell amount of blood comes here in this area, C3. You understand what I want to say? Okay, so this is very nice presentation of the experiments which we did. Also, we use this system, again here the NIRS system, here the EEG system, and we use it in OLAB. This is OLAB here. And we use it for some sleep study. You know, we ask from a student to do some memory task, really, to memorize some words, some relations, really, and then ask from him to get a nap, 1 hour or up to 2 hours sleep after the lunch, and then we ask to remember what he learned before sleeping, you know. And by this kind of registration, we understand that we did very nice job here. The paper will come in several months, maybe later, about memory consolidation. How you put something in your long-term memory. This is very important, very nice discussion at the moment. The role of sleep, it's very important, different stage of sleep, you know, and it has been a very nice project which we did based on EEG and NIRS, both technology. And normally in NIRS, in hemodynamic activity, when you record by the system, you have this kind of signal, you know, and this is the signal. It looks like much like a noise, but when you go in detail, you have many nice information. For example, if you open this part of signal, you have a beating heart, you have a heart rate here. Also, you have a respiration. You see here the respiration comes out, up, down, up, down. This is the respiration component. And also, mainly you have to, if you get a FFT Fourier transform from the signal, you have 3 main components. One component is around 1 Hz, 1.2 Hz, which is the related to heart beating. This is the heart rate. Around 0.3 hertz, you have a respiration signal, and low and very low frequency here, which is slowly comes up and down signal like this. It created the task, really, the task which is related to, for example, memory consolidation or something like that. It depends on which task you want to use this machine. Okay, I'm done my job. So if you have any question, please do not hesitate to ask it. We have sometimes more. Excuse me, I think it's become a little bit longer now. It becomes around 1 hour and 30 minutes, 25 minutes of presentation. Personally, I become tired. Most probably you have the same situation. So I'm ready.
We would to thank you for your nice presentation.
You are welcome.
It's really good and useful work.
You are welcome. Okay.
Actually, I enjoy it, although it's far from my major interest, but I enjoy it really.
You are welcome. Excuse me, Professor, because I understand that you are one of the professors in the university. You know, I have to reduce the level of presentation because the international department of our university, they said to me that the main participant will be the BS degree student.
Yeah. In fact, the attendance are mostly undergraduate and postgraduate students, in addition to some professors in the Department of Electrical Engineering, University of Basrah.
So sorry if it was not so useful for you, I know it, but I have to do something which can be useful for nearly everybody, especially for the main group, which has been the undergraduated, as you said.
Of course.
Okay, if you have any question or other participant, if they have a question, I'm ready to answer.
Yeah, I have one question, Dr. Jabal.
Yeah, you're welcome.
Yeah, you simulate the human head, right?
Yeah.
Did you use one computer performance, or you did a parallel computing process? Because it's usually take a lot of process from the normal computing to have simulate such meshing cells of the human head.
If I understand correctly, you are talking about data processing.
Yeah.
Extracting the result. Okay, you know that this type of data processing, we get it offline. Means during the online process, just we record data, just this, the raw data, you know. And in offline processing, normally there are several toolbox in MATLAB, for example, like Homer for near infrared spectroscopy, or like EEG lab for electroencephalography. Most probably you know it. And we generate this result, we get this result in offline processing, not online processing. Because as you said, this is a quite difficult task to get online signal from.
So usually how long it will take to get such results, like the simulation of the blood and the brain? Like the animation that you showed in your presentation?
Oh yeah. Okay. You know, we have for example, the simulation which I showed to you. I had one detector here, okay, in the left side, and 4 emitters just around. So we have one area here, and exactly the same area on the right hemisphere and the left hemisphere, both of them. Okay, and by data from these channels, each emitter and detector create one optical channel, and by processing this optical channel and make a kind of interpolation between this channel and this channel, for example. You see, I have one channel here, one channel here on the other side. So we can make a kind of interpolation between these channels, and by this interpolation, the animation like that, we can generate by MATLAB software, but in offline.
Okay. Thank you so much, Victor.
You are welcome. You are welcome. Okay, if you think everything is good and you understand everything, and if you don't have any other question, I can say goodbye and Khuda Hafiz. God bless you. Huh?
Thank you, Professor.
You are welcome.
Thank you, Doctor, so much. Thank you, Doctor.
You are welcome. It has been my honor to be in your university, not directly through the internet medium, and it was very nice also for me to make this kind of type of presentation. Hope it works for you. You understand. You get some idea from what I present. For sure, my presentation is nothing, just a kind of pushing to go inside to get some idea, you know. And later, for sure, you can go more in detail, more and more in detail, and you will be an expert in this area if you would like.
Doctor,
Okay.
Doctor, you can write your mail in chat, please.
Yeah, everything is in my presentation. Let me come back to first page. Yeah, here. You have here
Yes.
my email address. Also, you have my website address. You can scan this QR code. Everything is there also.
Thank you.
Yeah. My telephone number, if it's necessary. But at the moment, this is the fixed number of university, and at the moment, because of COVID, normally we are still at home and do our job at home, so I cannot answer this telephone. But by email, normally, always I'm online.
Thank you, Doctor. Thank you so much.
You are welcome. So have a nice time there, and Allah bless you.
Thank you very much, Professor.
Bye-bye.
Bye.
Bye-bye.